So this is the second half of chapter 1, and I'm going to pick up where we left off the other night. 3 states of matter we most commonly deal with in chemistry are gas, liquid, and solids. Starting at the bottom, solids are the most organized state of matter. Everything's usually in a regular geometric pattern. They are essentially incompressible, and they have a definite shape and definite volume. Liquids are slightly compressible. The molecules kind of slide past one another. There's a little bit of space between them. It has no definite shape but a definite volume. So whether I have 8 ounces of water in a glass or 8 ounces of water in a puddle on the floor, it's still 8 ounces of water, but the shape will change depending on the container. And gases are highly compressible because the molecules are always spread out in a random order, and gases expand to fill whatever container it's put into. So whether I have half a liter of oxygen gas in a 2-liter bottle or half a liter in a balloon, the molecules are going to spread out as far as they can in that container. So they have no definite shape and no definite volume. When we talk about forces between particles, solids have the strongest forces, gases obviously the weakest forces because they have the most entropy. They have the most randomness. As we learned the other night in lab, density is the ratio of mass to volume. The formula is density equals mass over volume. So density for a substance is a constant because if you change the mass, the volume changes proportionally. The most commonly used units are grams per milliliter if it's a liquid, or grams per liter if it's a solid. Sometimes you also might see grams per centimeter cubed. So here's an example. If 73.2 mils of a liquid has a mass of 61.5 grams, what is its density? And notice here they displayed the answer to the correct number of sig figs. You're dividing, the top value has 3 significant figures, the bottom value has 3 significant figures. Therefore, our answer has 3 significant figures. Leading zeros don't count, trailing zeros count when there is a decimal. Specific gravity is the density of a substance compared to water as a standard. It's a ratio of 2 densities, therefore it has no units. So if we know the density of copper at 20 degrees is 8.92, and we know that the density of water at the same temperature is 1, then the specific gravity of copper is the density of copper divided by the density of water, and the units cancel. Now this is different from comparing densities of different liquids like we did in the lab on the last part that I did as a demo. Substances with higher densities will layer at the bottom while substances with lighter densities will layer on the top. And the reason that's why ice floats in water is because the density of ice is actually less than the density of water. When we talk about chemistry, we need to talk about energy because most of the time, whether something's going from a solid to a liquid to a gas or vice versa, or if we're mixing 2 substances, energy is changing. So energy is referred to as the capacity to do work. So this can be kinetic or potential. Potential energy is stored energy. It's energy that's within a substance or an object while it's in that state or in that position. So a book sitting on a desk, that book has potential energy. Whereas kinetic energy is energy in motion. And as the object's velocity increases, the kinetic energy of that object also increases. So there's a direct relationship. At the same velocity, a heavier object is going to have a greater kinetic energy, and that's because the formula is equal to 1/2 mv squared, where m is mass. So the heavier the mass, you're increasing your kinetic energy, and then the v is your velocity. The calorie is the base unit of energy. However, we do and we will in our lab also measure energy in joules, and that's Joules, and it's the letter J. So be aware that those are the two units we will be using. There are all different types of kinetic energy. There's mechanical energy, so like machines, light energy, heat energy, and electrical energy. In chemistry, though, we are going to talk mostly about chemical energy. We will not talk about nuclear energy in this class. It might be mentioned at some point in time, but that's not our focus. Chemical energy is stored in chemical substances. It can be stored in food, such as carbohydrates and fats, and we're going to measure the energy in food in an upcoming lab. It's also given off when substances take part in chemical reactions. Well, it's not just given off. Energy can also be absorbed. So when we break bonds, we absorb energy, and when we make new bonds in new materials, we release energy. Whether energy is being absorbed or released, the total energy of a system is constant, and we refer to that as the law of conservation of energy. Energy can't be created or destroyed. It can be rearranged or converted from one form to another. So what one system loses in energy, theoretically, in an ideal system, another system gains. We're also going to study this in the lab. However, we're not going to have a perfect system in the lab because there will be some heat loss to the environment, okay, because heat travels from an area of higher temperature to an area of lower temperature. So if we're trying to measure energy and we're not in a closed system, and where we're trying to measure it from is higher than the surroundings, we're going to lose some heat from that system to the surroundings, or our lab room in the case where we're going to be studying. Heat is a form of energy. Heating refers to energy transfer when two objects of different temperature are brought to contact. So I just mentioned this. Heat energy flows from a hotter object to a cooler one until the two are equilibrium. We also measure heat in calories, and it's defined as the amount of energy needed to raise the temperature 1 gram of liquid by 1 degree Celsius. Calories not part of the system of international units. So the official SI unit of heat is the joule, which I already mentioned, which is about 1/4 of a calorie. So we talked about dimensional analysis and conversion factors during our first lesson. Remember, 1 foot is 12 inches, and we used a couple of others. 1 pound is 453.6 grams. So here's another conversion factor. 1 calorie equals 4.184 joules. Specific heat is the amount of heat necessary to raise the temperature of 1 gram of a substance by 1 degree Celsius. And let's look at the specific heat capacities for some of these substances. You can see that water has a pretty high specific heat capacity compared to other things like wood, glass. So this should make sense to you. If you've ever gone to a boardwalk or a beach in the summer and you walk barefoot, okay? When you're walking barefoot on wood, it's pretty hot. The wood's hot to your feet, but you can handle it. But then you step off into the sand and your feet start burning. and you run as fast as you can to the water. And then when you get to the water's cooler. Well, do you ever wonder why? Well, it's not listed here, but sand has a very, very low specific heat capacity. It's 0.19 calories per gram. So what that means is it takes very little energy to raise 1 gram of sand 1 degree Celsius. So it's going to get hotter more quickly than wood, which is still not going to be as hot as water, because water takes a very, very long time to get hot. That's why typically when we go to the beach, it's hot on the sand and cooler in the ocean, because it takes more energy to heat up the same amount of water as compared to sand. So the following equation gives us the relationship between specific heat, the amount of heat, the mass of an object, and the change in temperature. The units of specific heat are calories per gram per degree Celsius. The amount of heat is equal to the specific heat times the mass times the change in temperature. Now, I do want to point out that this is also written in a slightly different format. This formula can also be written as Q equals MC delta T. So Q is heat. So this might just say heat, or it could say Q is equal to the mass. You can see that the mass is the same in both these formula. Okay? But SH stands for specific heat, and in the chemistry formula, C stands for specific heat. And delta T, delta means change, so change in temperature refers to the T2 minus T1. So I'm not trying to confuse you, I'm just trying to point out that depending on what book you're using, what resource you're using, you may see the same formula written in slightly two different ways, and you need to be aware that they are the same thing. In our text, they use heat equals SH times N times T1, T2 minus T1. I believe in the lab they refer to it both ways. The Q equals MC delta T and the bottom one. So let's look at an example of how this formula works, because this is what we're going to be doing in the lab on Thursday. How many calories are required to heat 352 grams of water from 23 to 95 degrees Celsius? The specific heat of water is 1 calorie. So when I read a problem, I like to identify what it is that I've got. So this refers to my mass. This right here refers to my delta T, my change in temperature, and this is my SH, or my C. I label it as C because that's what I'm used to. So the amount of heat is going to be equal to the mass times the specific heat times the change in temperature, and you can see how they did that there. They multiplied all three and they solved for calories. When we come in on Thursday, I will review a couple of these problems at the beginning of class. So, as I just said, I would like you to try to do these 4 problems in your notebook, and I will review them at the beginning of class on Thursday, along with some other things that we covered in the first chapter. In order to do that, I would also like you to watch a very short lesson that starts chapter 2, which will be posted after this video.